Hello, I'm Shortao Zhu from MIT CSAIL. Today I'm going to present our work on AQUOMAN, an Analytic-Query offloading machine. This work is done with my advisor Professor Arvind, my MIT colleagues Thomas and Tianhao, and my collaborators Hongjun and Professor Li from DGIST. First, let's look at analytics on big data in the real world. Today, multi-terabyte or even petabyte analytics are very common. For example, in 2016, Uber generates 100 terabyte data daily and analyzes 100 petabyte data for business intelligence. Most systems nowadays still relies on SQL to run analytics. Typically, data are warehoused in column stores such as Apache Parquet and analyzed by SQL query engines such as Presto, Vertica, and MonadDB. To run fast SQL analytics, one will need fast machines. Let me demonstrate by using a single-node x86 server. Such a server is typically equipped with 1 to 5 terabytes of SSDs for data storage. The x86 host needs many cores to run compute-intensive analytics threads. It also requires a large amount of DRAM to provide fast access of cache data from the slow storage device. Such a solution is not only expensive but also power-hungry. So a natural question to wonder is that can we find an alternative by using a smaller host server without sacrificing query's performance? How about pushing SQL computation into storage device? Such a solution will require an in-storage processor or ISP inside the SSD for query offloading. If enough query processing could be offloaded to the ISP inside the SSD, one could in theory free up host hardware resources otherwise needed for query computation. This idea of pushing compute to data is not new. In the 80s, David DeWitt from Wisconsin has explored such ideas in the Gamma project. The key motive is to reduce I/O to compute, and a similar idea has been successful in the cloud. However, in-storage processing has not found traction commercially. Most systems only offload filtering, and we hypothesize it is simply not enough since filtering is not a computational bottleneck for the database. Another obstacle for ISP is limited compute and DRAM resources available. Typically, an ISP has embedded processors and/or FPGA and a limited size DRAM. Therefore, it is non-trivial to offload the complex operations such as join. Also, providing a good programming interface for ISP is not easy. Therefore, a database redesign in software and hardware is needed for offloading SQL computation near data. We propose AQUOMAN as such an in-storage analytics solution. AQUOMAN provides an end-to-end solution integrated into database system where you can run SQL queries transparently. It starts with a standard SQL query. The SQL query is firstly mapped into AQUOMAN table tasks, which is a programming model of AQUOMAN. And table task is a fixed data flow pattern of SQL operators, and it can be composed to map multi-way join. After the query is mapped to AQUOMAN table tasks, they are executed on the AQUOMAN microarchitecture. It allows streaming processing to use a smaller DRAM while saturating the flash bandwidth. AQUOMAN would require both software and hardware work. First, I will illustrate how to map queries on AQUOMAN by following two examples. The first example has one input table and sums up the net sale and revenue of each department before 1998 December the 1st. The first step is to apply filtering using the predicate for row selection. The second step is to apply table transformation, which converts rows of input tables to new rows for later processing. The third step is to aggregate rows per department, which can be also thought of applying reduction functions on each table partitions. In this simple example, you will see three steps of select, transform, and reduce. The second example has two input tables, and it computes the total sale of shoes sold after 2018 March 15th. This query needs to compute a so-called inner-equal join by matching inventory IDs of the tables. The first steps are applying filtering on the tables. The second step are extracting inventory IDs from respective tables which can be also abstracted as table transformation. We can see that the first two steps are the same as in the previous example. The third step is to merge if inventory IDs from the two tables are the same. This step also requires an invariant that input streams are sorted by the right key. With the two previous examples, we can see a common pattern of static data flow of three types of SQL operators: row select, table transform, table reduce, or merge. We can combine them as a super operator, which we call a table task. To process each table task, we can stream the intermediate results such that no DRAM is needed. Outputs of each table task is materialized on DRAM. We can compose table tasks for multi-way join by recursively merging two table task outputs. The query planner can simply identify the maximum subtree that can be mapped to table tasks. There are some trade-offs for query planning, such as ordering a multi-way join or read streaming table when DRAM is insufficient. However, query planning is not the focus of this talk. Now that we have learned how to map queries to table tasks, what kind of hardware changes, especially the microarchitecture support, are needed for AQUOMAN to execute them? First, let's look at how to change X80 system to support query offloading to AQUOMAN. To enable the usage of AQUOMAN, one will firstly need to modify the database management system software. One will first need to add an AQUOMAN compiler to do the AQUOMAN query planning. An AQUOMAN executor is also needed for offloading table tasks. In the SSD, you will also need added functionalities for AQUOMAN. First and foremost, you will need AQUOMAN accelerator as an ISP to execute table tasks. The accelerator shares a flash access with host legacy I/O stack. To use AQUOMAN, the software offloads table tasks to the SSD and later collect results. Now, what kind of e-storage microarchitecture is needed for AQUOMAN to run table tasks? AQUOMAN's microarchitecture is a fixed data flow pipeline of three key components, which maps the three SQL operators in a table task. The row selector, which executes filtering, the row transformer, which transforms tables, the SQL switch knife, which maps the table reduce or merge. I will not go into the details of each pipeline components due to time constraints. But if you are interested, please read our paper. Now, I have presented an overview of AQUOMAN's program model and microarchitecture, and they look quite general to run any queries. However, in real hardware implementation, there are some limiting factors which causes queries to be partially offloaded, and there are four of them. The first limitation arises when join operations exceed AQUOMAN's DRAM. The second limitation is due to the fact that AQUOMAN only stores row IDs and join keys to decrease memory footprint. This causes AQUOMAN unable to process queries after aggregate or top K operators. There are four such queries in TPCH, but they are generally okay because aggregate top K are typically at the end of a query plan. The third limitation arises when aggregate group by has too many groups and exceeds AQUOMAN's SRAM. In the TPCH, only Q18 has a significant side effect of spillover groups. The last limitation is due to extreme processing on large string columns, which causes small random reads and read amplification onto the flash drive. When AQUOMAN fails processing a query, it hands off to the host and lets the host finish the computation. You may be a little bit unsatisfied to see so many limiters for AQUOMAN, but in real workload, which you will see later, AQUOMAN can still offload the majority of query processing for TPCH. Now, let's evaluate AQUOMAN. Before showing you numbers, I will first describe how AQUOMAN is implemented. AQUOMAN was first implemented in FPGA, but we soon ran into several issues. First, the DRAM on our FPGA is too small to run all TPCH queries. Second, our design slightly exceeds a single FPGA's area, but a good engineering effort can easily fix this. Third, we don't have a regular expression accelerator, which has been done but still non-trivial. Last, manual compilation effort was just too high. To establish the usefulness of AQUOMAN and allow more queries to be evaluated, we implemented a trace-based AQUOMAN simulator, which is fully integrated into MongoDB software. It is validated against our FPGA implementation. To set up the experiments, we use 1 TB synthetic TBCH dataset. We ran all 22 TBCH queries in the benchmark suite on our system. The database software is a modified MongoDB. The hardware setup is as follows. On the host, we have a small setup mimicking a desktop machine, and a large setup is a server class machine. On the storage side, we have a baseline of 5 NVMe SSDs in RAID 0, and AQUOMAN disks with 2 different DRAM sizes, 40 GB and 16 GB. Now let's look at numbers. First, how much query performance can AQUOMAN offer? The orange bar shows the AQUOMAN processing time on a large host with standard SSDs, while the yellow bar shows a large host with AQUOMAN disk. Once a large host is equipped with AQUOMAN, it can boost query performance by 1.5 to 2x on average. A maximum of 70x speedup can be seen for some join-intensive queries on the baseline. Similar average performance measurements are also seen when a smaller host is equipped with AQUOMAN 16. An interesting finding is such that a smaller host plus AQUOMAN 16 performs as well as a large host with a standard SSD. Now, let's look at how much query processing can AQUOMAN offload. Just as we stated earlier in the presentation, although some queries cannot be fully offloaded, the majority of queries, 14 out of 22, are fully offloaded. 4 queries are partially offloaded due to group by, and the Q1718 still have significant speedups. Other 4 queries are not offloaded due to streaming processing on large columns. On average, AQUOMAN can save 69% of CPU cycles for TPCH benchmark. Lastly, how much memory can AQUOMAN free for an x86 host? A large baseline system requires a 128 GB maximum DRAM and 45 GB on average. Once it's equipped with AQUOMAN, the x86 memory usage for queries with high offloading percentage goes to near zero. The average memory decreases to 17 GB, but the maximum stays the same. This is because of Q18, which is the maximum memory consumer, is still partially offloaded. On average, AQUOMAN saves 60% of host memory. For AQUOMAN DRAM, it requires 38 GB for all queries. However, only 3 queries need more than 16 GB DRAM, which means an AQUOMAN with limited DRAM size is still very useful. To summarize, AQUOMAN Augmented SSD can speed up queries by 1.2 to 17x and offloads around 71% of the work, which saves 60 to 70% of host hardware resources. A way to visualize the benefits of AQUOMAN when page cache is ineffective is such that, on one hand, we have a server class machine with 32 cores, 128 GB RAM, and 1 TB SSD. To match its performance, we'll need a 1 TB AQUOMAN SSD and only a desktop class machine with 4 hardware threads and 16 GB DRAM. To conclude, I have presented AQUOMAN, an in-storage Analytic-Query accelerator which can offload the majority of query processing. I presented its programming model, the microarchitecture, and demonstrated its advantage. There is a lot more in our paper if you want to understand the details of AQUOMAN. Thank you for tuning in. If you have more questions, please feel free to contact us or find me after the talk.